Alright, welcome to Lecture 2, Lewis dot structures on our chemical bonding unit. In the previous lecture, we looked at covalent, metallic, and ionic bonds, how they're formed, and so forth. And this particular lecture is going to more or less focus on covalent bonding and how we structure the atoms, or how we connect the atoms together using dots to represent bonds or lone pairs of electrons, which we'll explain as we go through this. The essential question is, how do you draw a Lewis dot structure? Alright, to start us out with, we're going to look at what a Lewis dot structure is, what it looks like, and so forth. So the idea is a Lewis structure is a representation of atoms and molecules that show its outer electrons. This was done by Gilbert Lewis. And again, Lewis dot structures here to the most convenient way which chemists represent atoms, molecules, and ions. I'm going to give you an example of water. This is the molecular formula for water, H2O. But how do these atoms connect together? So in other words, we know that water is composed of oxygen and hydrogen. We even know the ratio is 2 to 1. But how do we bond them together and showing that they're covalently bonded? Well, the way we do that is we use dots. Something like this, where you have oxygen, 2 dots, and then hydrogen, another 2 dots and a hydrogen, and then we have some dots here. Alright, now this is the Lewis structure of water. Now, the dots that you see here are going to represent electrons, more specifically valence electrons from the outer shell. Alright, now there are 2 types of dots. The dots that you see in between the oxygen and the hydrogen are known as bonding electrons. Alright, and bonding electrons are just as simply what it says. They're electrons that form a covalent bond. And every covalent bond has 2 electrons that are being shared by 2 nonmetal atoms. You know that from last lecture. So we use those 2 dots as bonding electrons. The dots that you see here, these are not bonded to anything, so these are called non-bonding electrons. Non-bonding electrons, or a lot of times we'll call them a lone pair. Lone pair of electrons. And we're going to use this terminology, lone pairs versus bonding electrons, throughout this lecture and other lectures to come. And so you need to know this terminology. So what we're going to do for the rest of this lecture, though, is talk about how we actually form a Lewis dot structure. Alright, so there are some simple rules that we need to follow in order to draw a Lewis dot structure. I'm going to go through these really quickly, but it's going to be up to you to learn them, to know them really well, and be able to go in the order that we have here, 1 through 6. Okay, so first of all, the first thing we're going to do is you have to count up the total number of valence electrons for each of the atoms that are involved in the molecule. Total number of valence electrons. Alright, now I will give you a hint, you might want to write this down here, is that when you count up the total number of valence electrons for each of the atoms, the number needs to be even. If it is not an even number, then you cannot draw a Lewis dot structure for it. It has to be even. All right. If you have ions, so A and B here, if you have ions, If you have negative ions, so anions, then you add that number to the total valence and electron shell. So for instance, if you have a negative 1 charge, then you would add a 1 to the total number of valence electrons. If you have a negative 2, then you would add 2 valence electrons to the total number. If you had 3, then you add 3 and so forth, okay? But if they're positive ions, such as positive 1, then you actually subtract 1 electron. If it's a positive 2, then you subtract 2 electrons. Positive 3, you subtract 3 electrons, and so forth. Okay, so just keep that in mind as we count up the total number of valence electrons here. Now, after you've done that, then step 2 says you're going to determine the atom that's going to be central to everything else. Now, the central atom is the one that typically needs the most electrons to fill its outer shell. So you remember the goal for atoms is to have complete outer shells, to fill them. And the magic number is 8 and 2. Most atoms need 8 valence electrons to have a complete outer shell, and some of them need only 2. All right? So the element that needs the most electrons goes in the valent, or goes in the central. Okay? Now, step 3. Once you know your central atom, then you can make bonds between the central atom and the other atoms by using dots, kind of like we saw earlier how we use dots to represent a bond. So we showed that with oxygen here, where we had an oxygen, we used 2 dots, and then we bound it to hydrogen. And those dots then are step 3 to make a bond. And you're going to make bonds all the way around the central atom with 2 dots and the other atoms. All right. Now, once you're done that, then you go to step 4 and you're going to subtract 2 electrons from each covalent bond drawn in step 3 from the total number of valence electrons calculated in step 1. All right. So you're going to take all of the bonding pairs, or the bonding dots, and subtract it from our total number of valence electrons in the first step that we talked about there. Okay. Now, it's important to note that you are going to use up all of the valence electrons when you do this method. And so there shouldn't be any valence electrons remaining once you're done. All right? Okay, so now once you've done that, you go to step 5. Now, step 5 is simply this. You're going to distribute the remaining electrons as lone pairs around the rest of the atoms. Now, this is important, A and B. You must always put lone pairs of electrons starting on the outside atoms first. All right? You're going to always put them on the outside atoms, and then when they have a complete full outer shell, then you're going to add electrons to the central atom as lone pairs, but only do that last. Again, always put lone pairs on the surrounding outward atoms, and then you're going to work into the center and put lone pairs there on whatever's left over to get us a full, complete octet. Oh, by the way, the octet, what that means is 8. So the octet rule just means we have to have 8 valence electrons around the central atom. The duet rule just means that we only need to have 2 electrons around the central atom for it to be happy. All right? Now, step 6 says that if there's an atom, and this is really more the central atom, but if the central atom is deficient in electrons, so it doesn't have 8 electrons, then you're going to convert, and this is really important, you convert lone pairs from a neighboring atom into bonding pairs, and then you're going to create what are known as double and triple bonds. And I'm going to give you plenty of examples of this. So I just kind of went through these rules a little bit, but we're going to go through them and show you real examples here. And so what I would suggest that you do is we go through the examples of drawing several structures, that you have these rules out by your side, and we go through them. You'll also need a periodic table to do this as well, because you need to be able to count up the valence electrons for each one of these atoms. So get you out a periodic table, have your notes out on how to draw Lewis dot structures, and let's begin to practice these rules. All right, the first example, let's go back to water again, okay? And we've seen what the Lewis structure looks like for water, but let's actually draw that using our rules of H2O, all right? So rule number 1 states what? That's right, we got to count up the total number of valence electrons for each of the atoms. So if you look at your periodic table, you will notice that oxygen has exactly 6 valence electrons, and hydrogen has 1 valence electron, but we have 2 of them, so we'll multiply it by 2. So that's 2 and 6, add them up, and we have a total of 8 valence electrons for this. So step number 1, we know we have a total of 8 valence electrons, 6 from oxygen and 2 from the hydrogens. So I'm going to erase this, and I'm going to put total valence electrons is 8. That means we have to use up all 8 of these. Also, I'll note that it is an even number, and so we can do this structure because it's even. All right, so now we have to go to step 2. What is our central atom? Well, it's oxygen. Why is it oxygen? Because it needs more electrons in order to have a full shell. The hydrogen only needs 1 more, because it only needs to have 2 electrons to have a full shell. The oxygen needs 2 more electrons to have a full shell. And so oxygen is my central atom. All right? And so then step 3 says that we need to bond the rest of the atoms around the central atom using 2 dots to represent a bond. So there's 2 dots represents 1 covalent bond for one of the hydrogens, and another 2 dots to represent the other covalent bond. All right? So then the next step says we need to count up the total bonding electrons and subtract it from our original 8. And so we used up 4. So 8 minus 4 is 4. So I have 4 remaining valence electrons. So the next rule states that we're going to distribute the remaining electrons around the atoms to get us a complete full valence shell, or the octet rule. And so notice that the hydrogens already have 2 electrons that they're being shared. 1 and 2. So does this hydrogen need any more electrons? No, it has a full shell. So we don't need to add any more electrons to that hydrogen. The same thing with the other hydrogen. It has 2 electrons. And so therefore, that hydrogen has a full valence shell. But it's the oxygen that doesn't have a full valence shell. If you look at oxygen right now, it only has 4 electrons around it, representing the 4 dots. So now we're going to place the other 4 electrons as lone pairs. And so we have a lone pair here. That's 1 lone pair. And another lone pair there. That's 2 lone pairs. So now we've used up all 4 of those electrons as lone pairs. A lone pair here, here. And then we have 2 bonding pairs of electrons. and we've used up all of our total electrons. Now, does oxygen have 8 electrons around it? It sure does. It has 8 dots around it. 1, 2, you can count them. 1, 2, 3, 4, 5, 6, 7, 8. So oxygen has 8 dots around it, or 8 valence electrons, therefore it has a full shell. And each of the hydrogens also have full shells, so this is the correct structure. Now, sometimes scientists like to change the bonding electrons to lines like so. And so instead of using dots, they'll use lines. We'll still use dots for the lone pairs, but this is another way of representing the Lewis dot structure. You can use either one. We'll start probably using the line structure, but just remember that each line represents 2 electrons that are being shared there. Alright? So, let's take a look at another one, shall we? Let's look at ammonia, NH3. Let's see. Count up the total number of valence electrons. That's the first step. Hydrogen, each one has 1, so that would give us 3 for hydrogens, 3 hydrogens. And nitrogen has 5, so 5 plus 3 is 8. So we should have another 8. It's an even number, so we are good to go. Okay, which one's my central atom? Which one needs the most electrons? Use your periodic table to determine that, and you will find that nitrogen needs 3 more electrons to have a full shell. Alright? So therefore, nitrogen is going to be my central atom. Okay, then we're going to put 2 dots to represent our bonds. So we have 3 bonds because we have 3 hydrogens. And so now we used up how many bonding electrons? 6. So we're going to subtract 6 from 8. That leaves us 2 electrons remaining. The hydrogens, we're going to start on the outside first with the hydrogens to see if they need any more electrons. And do they? No, because there are 2 dots around each of the hydrogens, so they're fine. They have full shells. So the remaining 2 dots need to go on, well, yep, nitrogen. Nitrogen needs 2 more as lone pairs. So there's our lone pairs there. And so now, how many dots are around nitrogen? And you count them up. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons around nitrogen. Is nitrogen got a full shell? Absolutely. It has those 8 electrons or 8 dots around it. So the nitrogens and hydrogens are all happy, content. They all have full, complete outer shells. All right. We can do the line notation, where you put lines in for each of the hydrogens and nitrogen bonds, and then our lone pair like so. And there we go. Okay. Making a little bit more sense. Again, in class we'll do a lot more practicing of this, but this at least will give you a head start to thinking about drawing these Lewis dot structures. Alright, let's try another one. Let's do nitrogen, or oxygen, O2. Alright, so step 1, total valence electrons. Well, we have 2 oxygens, each of them have 8, so that gives us 16 total electrons. And it's an even number, so we can do it. Well, do we have a central atom? No, because they're both need the same amount, so we're going to bond both of those together by using a pair of dots. So that's the only bond that's formed, so that means we're going to subtract 2 from the 16. That gives us 14 remaining. So we need to place 14 remaining dots as lone pairs around our atom. So let's start with one of the oxygens. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wait a minute, did I get that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm short. Why am I short? Did I count the total number correct? 8 and 8 is 16. Right? 16. Because we got 2 of those, so 8 plus 8. Oh, wait a minute. What am I thinking? My bad. I'm thinking the total number. We got a total number of valence electrons. See, even I have to check it sometimes. So the total number of valence electrons, back up, oxygen only has 1, 2, 3, 4, 5, 6. So oxygen only has 6 valence electrons, so it only has a total of 12. That's where we went wrong. Okay, so now let's go and bond, and then go around 2, 4. So again, we're going to subtract 2, so we only have 10 left over. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Uh-oh. We used up all 10. Do we have a problem? We do have a problem. The problem is that one oxygen has how many electrons around it? 2, 4, 6, 8. So this oxygen is okay, but notice the other oxygen only has 2, 4, 6 around it. It only has 6 around it, so we're short of electrons. Now, we can't add any more electrons because, well, we don't have any more, because we can only use a total of 12. So we have a problem, and we're going to have to fix that problem. Let me show you how. So let's go back and rewrite all this. So this is where we're at. And this oxygen on the left is the one short in electrons. So what we're going to do is the very last step in your note says if you're short of electrons, then what do? Well, you're going to borrow a lone pair of electrons from a neighboring atom. So we're going to actually steal these electrons here, and we're going to put them here and create us a double bond. So now what that does is allows our oxygen to have 2, 4, 6, 8 electrons around it, and the other one also has 2, 4, 6, 8 electrons around it because they're sharing. Let me show this in the structure. It might look easier. We're going to put 2 lines to represent 2 bonds between those oxygens, and that creates a double bond. Plus we have lone pairs on each one, like so. And so now we have 8 electrons because of 2, 4, 6, 8, 2, 4, 6, 8, and everyone's happy to go. So sometimes we have to create double bonds, and if we're short of more electrons, we may have to create triple bonds. Alright, we'll show you more how to do that as we practice in class and so forth. Alright, let's see one more example. Alright, SO2. Alright, so step 1, total valence electron number. Sulfur is going to have 6. Oxygen has 6. We have 2 oxygens there. So we have a total of 18 valence electrons that we're going to have to use. And it's an even number, so we're good to go. Alright, so what's my central atom here? Ooh, well, if you look at the periodic table, you would find that both sulfur and oxygen need 2 more electrons to have full shells. Uh-oh. So they both need the same number of electrons. So which one's going to be my central? Well, the way I want you to remember this is is the atom, if they both need the same number of electrons to have a full shell, then go with the atom that is that has more energy shells. Let's put it that way. That has more energy shells. And so in this case, sulfur has more energy shells than oxygen. So we're going to put sulfur as our central atom. And then we're going to bond the oxygens to the sulfur. And so we've used up now 4 electrons, right? So 18 minus 4 then is going to give us 14 remaining. And where are we going to distribute these 14 electrons? We're going to distribute them as lone pairs. And we must do so on the outer atoms before we do the central. Alright, so we're going to start on the oxygens first. So 2, 4, 6, 8, 10, and 12, and then 14 on the central atom, because we got to go one more. We got two electrons left over. Now we'll put on the central atom. All right, so let's see. Does everyone have an octet? Complete full valence shell. The oxygens, let's count those. We have 2, 4, 6, 8. So that oxygen is great. 2, 4, 6, 8. That oxygen is great. Now let's look at the sulfur. It has 2, 4, 6. Uh-oh. Sulfur is not good. It only has 6 valence electrons, not 8. So sulfur still doesn't have a full shell. So what do we do? Do you remember? That's right. We're going to steal a lone pair of electrons from oxygen and make a double bond. All right. Now, does it matter which oxygen? No, absolutely not. So let me re-erase this and rewrite this up. Now, so this is what we have so far: sulfur, oxygen, those lone pairs around the oxygen, and then one lone pair on the sulfur. So we're going to steal a lone pair there, and we're going to create a double bond there. And so if I were to show lines, it would look like this. We still have these dots. And the lone pair there. And now what we have is a double bond there. Alright, so there's our Lewis dot structure for this. Alright, so there's several examples we've gone through. And again, kind of get an idea, a feel of how Lewis dot structures work. Go through the rules, really learn those rules. Those are going to be really important for you to know for the quiz, those rules. We'll practice this in class to get better at this and answer any questions that you have. All right, but let's sign off for now. I think that's enough for this lecture. So good luck, study hard, and we'll see you in class.